A tsunami is coming. Time to live or die. The term tsunami, synonymous with tidal wave, comes from the Japanese Tsu-Nami, meaning harbor wave. A tsunami refers to an abnormal and massive ocean wave originating from a violent underwater earthquake or other events involving a sudden displacement of a large mass of water, such as a massive landslide or an underwater volcanic eruption. Usually, a tsunami forms in open sea where, however, the wave remains relatively weak and inconspicuous, gaining strength only near the coast when the wave, due to friction with the increasingly shallow seabed, rises and rushes inland as a true wall of water. Unlike traditional ocean waves, which are produced by wind and currents, a tsunami acts as an intense underwater disturbance, involving the entire column of water, from the seabed to the surface. The water displacement produced gradually propagates on the surface, creating very long surface waves, even a few hundred kilometers long, which extend across the ocean surface, similar to when you throw a stone into a pond. Just to give you some numbers, tsunami waves, when crossing a vast expanse of ocean like the Pacific, can have lengths of about 250 to 300 kilometers, reaching impressive propagation speeds of 600 to 700 kilometers per hour. Out at sea in the deep ocean on the very deep seabeds, the height of the waves is rather modest and often doesn't exceed 1 meter. So if you were out in the open sea, you wouldn't even notice the phenomena occurring. However, when the tsunami approaches the coast, the shallower seabed creates friction against the underwater disturbance, gradually slowing it down. As this happens, the principle of conservation of energy tends to greatly increase the height of the wave, thus favoring the formation of a real wall of water that crashes forcefully onto the shores, in the form of a series of large waves that penetrate inland for kilometers. However, a tsunami does not always present itself as a growing wall of water rushing ashore. In some instances, depending on the characteristics of the seabed, the wave may appear more like a large high tide, flooding the land for several kilometers where extensive plains are present. The area most affected by these phenomena is the Pacific Ocean, where most events occur along the circum-Pacific belt, often also called the Ring of Fire due to the presence of a large number of active and non-active volcanoes, some of which are among the largest in the world, such as Mount St. Helens in the USA, Popocatépetl in Mexico, Cotopaxi in Ecuador, and Mount Fuji in Japan. Along this ring, 8 tectonic plates converge with the large Pacific Plate, the Nazca Plate, and the Cocos Plate. The 5 strongest earthquakes in the last 100 years have generated equally destructive tsunamis, 4 of which occurred along the Pacific Ring of Fire in Chile, Japan, and Alaska, with the sole exception of the 2004 Sumatra tsunami, which instead hit the Indian Ocean. Large-scale tsunamis are very rare as they require earthquakes with magnitudes close to or exceeding 8. Earthquakes of such magnitude have an average frequency of about 1 per year. Considering also that approximately only 1 in 10 of these earthquakes occur below or near an ocean, and thus under conditions to generate a tsunami, it can be said that very significant tsunamis occur on a global scale, with a frequency of less than or equal to 1 every 10 years. It's truly a frightening thought. But how do these monsters manage to form? Whatever the cause, the formation of a tsunami is always linked to the sudden movement of significant volumes of rock material on the seabed. In 80% of cases, this occurs due to the triggering of an earthquake caused by the collapse of a submarine fault. In the 20th century, there were numerous seismic origin tsunamis, just to mention the main ones. November 5, 1952, a powerful magnitude 9 earthquake off the coast of Kamchatka generated waves over 18 meters high, causing an estimated 15,000 casualties. However, there isn't much information about this tsunami. The then USSR did not disseminate news and data, keeping most of the information secret, with the first news arriving only years later. This is also why the event is remembered as the Secret Tsunami. May 22, 1960. Chile was hit by the strongest earthquake of the 20th century, known as the Valdivia earthquake, 9.5, which triggered a violent tsunami with waves 15 to 20 meters high on the coasts near the epicenter. It reached Hawaii about 15 hours later with waves over 10 meters high, and after almost 24 hours, it also hit the coasts of Japan 10,000 kilometers away with waves of 6 meters. March 27, 1964. A magnitude 9.2 earthquake struck Alaska, generating a tsunami with waves that reached Hawaii and extended along all the Pacific American coasts and California. Only the sparse population density of the region prevented a higher death toll. Another possible trigger of a tsunami is landslides, which occur in 11% of cases. When a portion of a mountain near the coast collapses, the volume of rock that falls into the sea displaces significant volumes of water. Curiously, the highest tsunami wave ever measured occurred on July 9, 1958, in Lituya Bay, Alaska, precisely due to such an event, namely a gigantic landslide, where about 30 million cubic meters of rock fell into the sea, raising an enormous mass of water. The wave that followed reached an incredible height of 525 meters. Tsunamis induced by landslides are nonetheless more localized phenomena than those produced by major earthquakes, and even though, as we've just seen, they can reach exponential heights, the waves, always individual, travel short distances before crashing onto the shores of bays, fjords, or even lakes. In terms of importance, statistical calculations then prioritize submarine volcanic eruptions, which contribute only 6% to the triggering of a tsunami. During these events, there are violent outbursts of volcanic material and gas that, in some cases, manage to displace large amounts of water. But can all submarine volcanoes create tsunamis? Actually, no, because the energy of the eruption tends to dissipate in the water column. A concrete tsunami risk would only occur for those volcanoes whose peak is less than 500 meters from the sea surface. A modest percentage of risk, 3%, is then attributed to so-called meteotsunamis, or tsunamis, much weaker than others, caused by rapidly moving meteorological events, such as severe storms, gusts, and other storm fronts. At this point, some of you may wonder about the absence of mention of one of the most popular natural disasters among catastrophists: asteroid impacts. The absence can be explained by the fact that in recent history, it has never happened that a tsunami originated from the fall of an object from space. Or at least we've never had evidence of it, except in the case of the event 66 million years ago that led to the Great Cretaceous extinction. But that was indeed a truly unique case, statistically insignificant. But how is the intensity of a tsunami measured? Is there a scale like for earthquakes? First of all, it's important to make a clarification. The destructive capacity of a tsunami, as with earthquakes, depends not only on its intensity but also on the type of coast it hits and the vulnerability of the area, namely its propensity to suffer damage and the exposed value, number of units of each of the elements at risk: human lives, infrastructure, economic activities, natural resources, etc., present in the area in question. The highest tsunamis in history, for example, occurring in uninhabited areas, have produced very few casualties and even fewer material damages. Conversely, tsunamis just a few meters high have caused thousands of casualties and damages worth billions of dollars. The new tsunami intensity scale, introduced in 2001 by Papadopoulos and Imamura, incorporates 12 divisions and is consistent with the 12-grade seismic intensity scales. The new scale is arranged according to the effects on humans, nature, and objects, including vessels of variable size, and on buildings and other engineered constructions. 1. Not felt. Not felt even under the most favorable circumstances. No effect, no damage. 2. Scarcely felt. Felt by a few people on small vessels, not observed on the coast. No effect, no damage. 3. Weak. Felt by most people on small vessels. Observed by few people on the coast. No effect, no damage. 4. Largely observed. Felt by all on small vessels and by few people on large vessels. Observed by most people on the coast. Few small vessels move slightly on shore. No damage. 5. Strong. Felt by all on large vessels and observed by all on the coast. Many people are frightened and run to higher ground. Many small vessels move strongly offshore, with some crashing into each other or overturning. Traces of sand layer are left behind under favorable conditions. Limited flooding of cultivated land. 6. Slightly damaging. Many people are frightened and run to higher ground. Most small vessels move violently on shore, some crashing into each other or overturning. Damage and flooding occur in a few wooden structures, while most masonry buildings withstand. 7. Damaging. Most people are frightened and try to run to higher ground. Many small vessels are damaged, and a few large vessels oscillate violently. Objects of various sizes and stability overturn and drift. Sand layers and accumulations of pebbles are left behind. A few aquaculture rafts are washed away. Many wooden structures are damaged, with a few being demolished or washed away. Slight damage and flooding occur in a few masonry buildings. 8. Heavily damaging. All people escape to higher ground, with a few being washed away. Most small vessels are damaged, with many being washed away. A few large vessels are moved ashore or crash into each other. Erosion and littering occur on the beach. Extensive flooding ensues. Slight damage occurs in tsunami-controlled forests, stopping drifts. Many aquaculture rafts are washed away, with a few being partially damaged. Most wooden structures are washed away or demolished, with moderate damage occurring in a few masonry buildings. 9. Destructive. Many people are washed away. Most small vessels are destroyed or washed away. Many large vessels are violently moved ashore, with a few being destroyed. Extensive erosion and littering occur on the beach. Local ground subsidence and partial destruction in tsunami-controlled forests are observed. Most aquaculture rafts are washed away, with many being partially damaged. Heavy damage occurs in many masonry buildings, with a few reinforced concrete buildings suffering moderate damage. 10. Very destructive. General panic ensues, with most people being washed away. Most large vessels are violently moved ashore, with many being destroyed or colliding with buildings. Small boulders from the sea bottom are moved inland, and cars overturn and drift. Oil spills and fires start, with extensive ground subsidence observed. Destruction occurs in many masonry buildings, with heavy damage occurring in a few reinforced concrete buildings. Artificial embankments collapse and port water breaks are damaged. 11. Devastating. Lifelines are interrupted and extensive fires break out. Water backwash drifts cars and other objects into the sea, with large boulders from the sea bottom being moved inland. Total damage occurs in many masonry buildings, with a few reinforced concrete buildings suffering destruction and many suffering heavy damage. 12. Completely devastating. Practically all masonry buildings are demolished, resulting in total damage. Most reinforced concrete buildings suffer at least heavy damage. As you can see, the definition of an intensity scale does not rely on physical parameters of the natural event, but only on observations regarding the degree of impact of the event. For example, earthquake intensity scales are not arranged based on ground velocities or accelerations or other physical characteristics of the earthquake. So it is quite impossible to correlate intensity degrees with physical parameters like the single wave height. Alright, but what can be done in terms of prevention? Can we or can we not minimize the damages and casualties caused by such extreme natural phenomena? Well, first of all, it's worth mentioning that while effective procedures for active prevention of earthquakes on the territory can be implemented through the construction of infrastructure and buildings with rigorous anti-seismic norms and techniques, for tsunamis, direct protection is not possible. Since tsunamis are long waves of enormous scale, any reasonable barrier erected along the coast would be overwhelmed and overcome by the immense force of the wave. Therefore, since it is not feasible to effectively prevent any kind of material damage, the only possible form of prevention against tsunamis is passive protection, namely the activation of prediction systems and subsequent alerting of populations. Although numerous experiments are underway to determine a reliable physical mathematical model capable of correlating the occurrence of a tsunami in a certain and effective way, there is currently no reliable model in this sense. The only effective way so far to detect the actual generation of a tsunami by a submarine earthquake is direct measurement of the sea level variation immediately after the earthquake detection. Currently, measurements for early warnings with the necessary level of reliability can only be made using systems positioned on the seabed capable of transmitting acquired data in real time. However, this means that due to the high propagation speed of the tsunami over deep seabeds, and assuming at least 1 hour of advance warning, it is necessary to deploy wave detection platforms at a distance of no less than 1,000 kilometers from the coast that needs to be protected and alerted. Many cities overlooking the Pacific Ocean, mainly in Japan but also in Hawaii, have long had alarm systems and tested evacuation procedures in case of severe tsunamis, while other coastal areas at risk are still uncovered. Following the catastrophic events of December 2004, the Thai government immediately unanimously approved a proposal for intervention for the prevention of such disasters and formulated a systematic program for the evacuation of areas in coastal provinces. The evacuation program included the installation of a public immediate alarm system and the indication of gathering points and shortest evacuation routes from the beach area. In a pilot project, an immediate alarm system was installed at 3 strategic points along Patong Beach, the area most affected by the 2004 tsunami. Subsequently, the installation of immediate alarm systems was carried out in each of the 6 southern provinces of Thailand. Data on the intensity of a possible wave caused by a hypothetical earthquake or tsunami will thus be processed and transmitted to the alarm system immediately via satellite. And in any case there is a high probability of a tsunami occurrence, an immediate alarm will be launched to high-risk areas around Thailand. Warning and alarm systems consisting of sirens, flashing red lights, as well as pre-recorded audio messages in various languages will immediately come into operation. The alarm system will be supported by radio stations and the automatic sending of over 20 million SMS messages. So far, these preventative measures have proven to be somewhat effective, but the problem arises when the seismic event occurs near the coastline, as happened in Japan in 2011. In this case, any attempt to alert the population could be inconclusive given the rapid propagation of the wave, and the only possible solution would be not to build settlements and inhabited centers of any kind along the coasts up to several kilometers inland. A bit like what the ancients did, especially the populations of the many archipelagos of the Pacific and Southeast Asia, who, knowing the risk very well, built their settlements beyond the mangrove forests. Okay, it seems like we're finally getting proactive when it comes to prevention, but the real question is, what to do if, despite everything, we find ourselves face to face with death? How to escape it? The main risk factor of a tsunami, we know this by now, is its unpredictability, being in most cases associated with earthquakes that in turn are not predictable. Moreover, when a tsunami approaches the coast, it is not a wall of water that we see coming from afar. What is initially observed is a rapidly rising tide, and the fact that it is far from the coast provides little perception of the size and speed with which it is approaching. Fortunately, before facing the wall of water, we can observe the phenomena of the gradual retreat of the waters. In the absence of an alarm system, this is the only true warning sign of the arrival of a tsunami. The retreat occurs approximately 5 minutes before the wave and is very noticeable, with the water moving away from the coast for tens of meters, even leaving boats stranded on the seabed. If you ever happen to see such a phenomena, the first thing to do, if possible, is to move away from the coastal area, lagoon surfaces, or other bodies of water, and go to a higher location at least 30 meters above sea level. On foot if possible, because most likely thousands of other people will try to leave in cars at that time. Despite its speed, the long wavelength of tsunamis makes the period of these waves very long. It can happen that many minutes pass between the arrival of one wave and the next, and that the tsunami lasts for several hours. Therefore, once you have found a safe refuge, do not trust to go back after the passage of the first wave. If you cannot go inland because access is blocked, quickly choose to climb somewhere. If the area has already been hit in the past by similar phenomena, it is likely to be equipped with so-called evacuation towers, solid lattice structures about 30 meters high with a platform that can accommodate hundreds of people. In the absence of these structures, head to a multi-story building as soon as possible, taking care if possible to choose one of the most solid. Other advice, as you can understand, would be entirely useless if the situation were already compromised and you suddenly found yourself struggling among the waves. In these cases, survival depends solely on individual ability to survive at all costs, and a lot of luck. There are countless earthquakes every day, ranging from tremors recorded only by instruments to shakes felt by the population. But But where do earthquakes occur? Are there specific areas or do they originate randomly? We'll seek to answer these questions, exploring not only how earthquakes form, but also why certain areas have a higher seismic risk than others. We'll then conclude with a roundup of useful tips for those unfortunate enough to find themselves living in a highly seismic area. Before discussing earthquakes, we need to provide some background on tectonic plates. What exactly are they? The Earth's crust is the outermost layer of our planet, and like a puzzle, it is divided into many plates, the famous tectonic plates. The interesting thing is that these plates are not stationary but can move over geological time. We're talking millions and hundreds of millions of years. Usually, earthquakes occur along the edges of these plates, which we can more accurately define as plate boundaries. But why do earthquakes occur precisely in these zones? Each plate has well-defined geographical boundaries, and when they move, they can interact with each other in different ways. They can collide, move apart, or slide past each other. Where they collide, compressive zones, for example, thrust faults will form, whereas where they move apart, extensional zones, normal faults will form. Even when two plates slide past each other, oblique motion faults are created, called strike-slip faults. When the two blocks of a fault move, earthquakes are triggered. So, in summary, we can say that it is possible to predict where areas have more earthquakes, namely the plate boundaries. If we compare these boundaries with the distribution of earthquakes in recent years, it is clear how the two perfectly overlap. For this reason, if we hear about an earthquake in Peru, from a scientific point of view, we shouldn't be surprised. It's quite normal since it lies along a plate boundary. Same goes for Japan, which unfortunately sits at the intersection of 4 different plates. But beware, outside of the plate boundaries, earthquakes are certainly rarer, but there are no seismic-free zones. There are high seismic hazard areas and low seismic hazard areas, where, however, an earthquake can still occur from time to time. An example is New Madrid, where, as explained in our video, the American town lives in an anxious anticipation of a big one, despite being distant from any fault lines. Earthquakes are by far the most powerful natural events on Earth. Quakes can release in seconds an energy greater than thousands of atomic bombs combined. Consider that an earthquake can move volumes of rock of hundreds of cubic kilometers in just seconds. It is estimated that about 500,000 detectable earthquakes occur on Earth every year. However, we humans can only perceive about 1/5 of them. The strongest earthquakes occur more frequently along the so-called Pacific Ring of Fire, in places like California and Alaska in the United States, El Salvador, Mexico, Guatemala, Chile, Peru, Indonesia, the Philippines, Iran, Pakistan, Turkey, New Zealand, and Japan. Between 1 degree and the other on the Richter scale, there's a ratio of about 1 to 10, meaning that, for example, there are about 10 times more earthquakes above magnitude 4 than those of magnitude 5. For each incremental increase in magnitude, there's also an increase of about 30 times in the released energy. For instance, a magnitude 6.0 earthquake releases about 32 times more energy than a magnitude 5.0 earthquake, and a magnitude 7.0 earthquake releases 1,000 times more energy than a magnitude 5.0 earthquake. As a result, earthquakes can cause severe devastation and high loss of human lives through a series of destructive agents. The main one being the violent movement of the ground, which can occur with accelerations that can be categorized as horizontal and vertical, resulting in the stressing of building structures, possibly accompanied by other stationary effects such as flood, dam collapses, ground collapses, landslides, avalanches, or liquefaction, fires, or release of hazardous materials. If the earthquake occurs beneath the ocean or near the coastline, it can generate tsunamis. In every earthquake, one or more of these agents can contribute to causing further severe damage and casualties. The strongest earthquakes, such as those in Indonesia in 2004 and Japan in 2011, can even shift the geographic North Pole by a few centimeters due to the elasticity of the Earth's crust. All of this, you'll agree with us, is truly terrible and deeply frustrating. No one enjoys feeling completely at the mercy of the elements. But is it possible that earthquakes still cannot be predicted? Unfortunately, the answer is still negative. Although it's true that some earthquakes, especially the strongest ones, are preceded by unusual natural phenomena called seismic precursors. There are countless testimonies, in fact, from people who, before a strong seismic event, parks where they saw flashes or glows or observed unusual behavior in animals. Moreover, instruments have recorded sudden variations in the local magnetic, electric, or radioactivity fields due to the emission of radon gas, interference in radio communications, variations in the water table level or coastal waters, etc. Since the 19th century, variations in the height of the water table and local gravity force, as well as radon emissions, have been studied. However, at the current state of knowledge, models have not yet been developed that allow us to highlight signals useful for the effective prediction of an earthquake, or its possible characteristics, intensity, and spatiotemporal localization. Increasing radon emissions, for instance, though somehow linked to a future potential earthquake, represents just an assessment of how likely the event might be. And without almost absolute certainty, implementing extreme preventative measures like ordering the evacuation of an area becomes really challenging. Even monitoring any seismic swarms preceding a main event often doesn't seem to yield tangible results in terms of prediction, as the vast majority of seismic swarms either resolve without causing catastrophes or dissipate more or less slowly over time. In the current context of seismological research, the most concrete results for earthquake prediction are obtained through long-term statistical analyses, consulting risk maps that consider the return times of an earthquake in a particular area, or calculating the probability of its occurrence. However, the time interval in which an earthquake is considered likely to occur is rather broad, even spanning decades, rendering any reasonable attempt at prevention that allows for effective population evacuation futile. In short, we must accept the fact that there is no scientifically valid method to predict earthquakes in advance. That's why the only solution for defense is to intervene preventatively on existing buildings with systematic measures that secure them, preventing collapse in the event of an earthquake. Seismic risk, in fact, can only be mitigated through preventative structural reinforcement interventions on the most vulnerable buildings. Of course, if it were possible to achieve this, it would come at an extremely high cost and with very long implementation times. And it is precisely this consideration that condemns developing countries to pay the highest toll in terms of human lives. At this point, many of you might be wondering, okay, but is there anything truly useful I could do to save my life if I suddenly found myself caught in an earthquake? Well, first and foremost, it is important to admit that all safety measures and advice found online are only valid in probabilistic terms, meaning that their application increases the overall survival rate of a population sample by a few percentage points, but cannot guarantee anything at an individual level. However, the behavior to adopt depends on the situation, the time of day, whether you're inside or outside a building, and many other factors. So giving advice is pointless because, at that moment, instinct often guides actions. If you find yourself in the midst of an earthquake, you often only have a quarter of a second to decide what to do. In general, one should simply consider that the main risk comes from the collapse of the structure you're in at the moment, along with the falling of furniture and belongings inside. Therefore, it's crucial to identify, obviously well in advance, what might be the most solid points of the structure, usually load-bearing parts, door frames, doorways, and corners, and position yourself nearby. The first rule, in our opinion, is to get under a sturdy table or bed. The idea of standing under a door frame is just a misconception. People choosing this position would commonly be crushed to death if the door jambs were to collapse under the weight caused by the earthquake impact. You're safer under a table than under a door, especially in modern homes. If possible, stay away from glass, windows, exterior doors and walls, and anything that might collapse like lighting fixtures or furniture. And especially if you're on a high floor, don't try to use the elevator or venture down the stairs. Stairwells and elevator shafts are the weakest structures in a building. If you find yourself outdoors, the main danger comes from what might collapse, so be careful not to linger or pass under parts of buildings, balconies, cornices, gutters, etc. that could fall. Instead, seek out a clearing or square that keeps you as far away from buildings as possible. A car can provide good shelter, so it's advisable to stay inside one as long as it's not parked under buildings, viaducts, billboards, or power lines. In a seaside city, it is possible that significant waves may occur following an earthquake, moving very quickly. These waves pose a real danger to those near the coast. so it's advisable to stay away from beaches for several hours. There's not much else you can do to avoid increasing the risks of other negative consequences, which only professionals can better assess how to manage. Besides, in such a situation, there's too much unpredictability to afford to waste time doing other things that might seem useful at the time. Gathering some important belongings, turning off electricity, gas, etc., but could exponentially increase the risk of further dangers, far from being decently manageable in that situation. Keep calm if you're trapped under rubble. Although it may seem counterintuitive, waiting for rescuers to arrive is the best choice if you find yourself trapped under debris you can't move. Don't use matches or a lighter. Gas leaks and other flammable chemicals could accidentally start a fire. Don't stir up or lift dust. Cover your mouth with a handkerchief or item of clothing. Bang your hand on a pipe or wall so rescuers can locate you. Use a whistle if you have one nearby. Shouting should be a last resort because it can make you inhale dangerous amounts of dust. And speaking of the whistle, well, one can't expect you to always have one on you, but a really useful tip could be this. If you live in a seismic area, try to keep a survival kit in your car and one close at hand at home. A blanket, water, a first aid kit if you can, a flashlight or headlamp, scissors, a phone charger charged, and, indeed, a whistle. Of course, always hoping it will never be needed.